Hello, and welcome to video 3 of the FP3 chapter Matrices. On the screen, start a question as usual. Pause the video if you've got time, and I'll go through the answer. Find the determinant of A using this formula here. So the determinant of A is equal to, we do these three elements in order, so 1 times 4, 1, minus 1, 0, minus 3 times 0, 1, 2, 0, plus 1 times 0, 4, 2, minus 1. To do these determinants, we do A times D minus B times C. So we've got 4 times 0 minus 1 times minus 1. 0 minus 2, 0 minus 8. So we get 1 plus 6 minus 8, which is minus 1. And we'll use that in our process in this video, because we are going to find the inverse of a 3x3 matrix, and in that process the first thing we do is find the determinant. So I'm going to walk through this process. It's long, it's kind of complicated, but don't get too worried because it is very systematic. You just follow the process, get the answer. There is not a lot of problem solving. If you can follow the process, it'll be fine. So here we go. We need to know this thing called a minor, and that is what we've already been using. It's a 2x2 determinant left when you cross out the row and column of the element you're looking at. So we've been using this because of the determinant of a 3x3 matrix uses these. So the element A here, the minor of that element is the determinant of EFHI. And we've used the top 3 elements and the minors of each of those elements. But you can do this with any of those elements. For example, H. Do the same thing, cross out the row and the column that has that element in it, and you use the remaining 4 elements in the order given, A, C, D, F, to produce the determinant you need. And then of course AF minus CD, and that is the minor for element H. And that's important because we're going to use the minor for every element in the matrix as part of finding its inverse. So here we go. 5 steps. First step, find the determinant of A. Going to use this example matrix because we already know the determinant from the starter question is minus 1. Step 2. Find the matrix of minors of A. So what we have to do here is use the minors for every element in this matrix and create a new 3x3 matrix of the minors. And we already know the first 3 because of the work we did finding the determinants. You might not remember them, but they were there on the first page. We had a 1, that was the determinant of the matrix left when we crossed out this row and column here. So 0, minus, minus 1. And these 2 were the minors for these 2 elements here. But you have to keep going. So for this element 0, that's going to go here. Cross out column and row with that element in, and you are left with a 3, 1, minus 1, 0. 3, 1, minus 1, 0. Then you have to do that 3 times 0 minus 1 times minus 1 to get the minor for that element here. And if you do that with all of these 6, this is the matrix of the minors. That's a long process, but we're not finished yet. Step 3 is to take these minors and find the matrix of cofactors. And how we do this is we apply this pattern here to the matrix of minors. Now it's not saying this has to be positive, this has to be negative. What it's saying is don't change this one, do change this one. So the elements of the minor matrix in these positions will be changed, i.e. we'll be applying a negative to them. So here, -2, if you apply a negative to that, it becomes +2. This will become +7, and we need these two as well, so this will become -1, and so will this. But the other 5 in the cross here, these will not change. So these 3 will remain negative, and this one will remain positive, like this. So these 4 have a negative applied to them, and the rest don't change. There is a reason for that, but we don't need to go into where this comes from. You just need to be able to apply it to get the cofactors matrix. But we're not finished yet either. Step 4 is to find the transpose of this matrix, which are the cofactors of this matrix, which are the minors of the original matrix A. Transpose is fairly easy, we've done that before. Turn the columns into rows, and we get this. And we're almost finished now, because the last step is to put your determinant together with the transpose of the cofactors. In the usual sort of way, we have a 1 divided by the determinant of A. From your 2x2 work, you remember that, and we're going to multiply it by this matrix. So in our example here, this is our transpose of our cofactors, and from step 1 we had -1 right back at the starter question for the determinant of this matrix. 1 divided by -1 is -1. -1 times this matrix applies -1 to each element. So our final inverse matrix of A is here. And I'm sure you can appreciate that that is a long process. But, like I said, no problem solving as such, you just follow the method. Summary. Step 1. Find the determinant of A. Step 2, find the matrix of minors of A, and don't forget, in your process of finding this, you'll find 3 of these anyway, so don't do that work again, just find the other 6. Then apply this to your minors to get the cofactors, change the sign of the elements in these 4 positions. Then find the transpose of that matrix, and multiply it by 1 over the determinant of A. So full example here, little cofactors pattern in the corner. First, the determinant of A. We have 5 times 8173 minus 0 times -1, 163. And if we just wanted the determinant, I wouldn't calculate that, but I'm going to calculate that because that will be the minor that I'll use in the next step anyway. So it's worth knowing what that is. Plus 2 minus 1, 8, 6, 7. So we've got 5 times 24 minus 7 minus 3 minus 6 minus 7 minus 48. So I'm going to calculate the brackets because they are the minors for each of these elements. So here we've got a 17, here we've got a -9, and here we've got -55. So these 3 numbers are 3 of my minors, so it's worth noting those to one side. The determinant then, put that on my calculator. Gives me -25. Okay, our minors, we need to continue this matrix here at the bottom by finding the minors for all of the other elements in the matrix. So I'll show what I'm going to do with the laser here, and then I'll just write in the numbers as I go. So I want the element here, -1. So I'm crossing out this column and this row. That leaves me a 0, 2, 7, 3. The determinant of that, 0 times 3 is 0, minus 2 times 7, minus 14. So the minor there is minus 14. And of course you could write out the determinant and the process and the answer, but if we do that with 6 of these, it's going to take quite a long time. So I'm going to just skip ahead like this. This element here, cross out this, 15 minus 12. 15 minus 12 is 3. Next one, cross out this and this. 5 times 7, 35, minus 0. One down here, cross out this and this. 0 minus 16. For the 7, cross out these, we get 5 minus minus 2. And the last one in the corner, cross out this and this, we get 5 times 8, 40, minus 0. So here are the minors, and as you get used to doing that process, it gets a little bit quicker. Now, we need to apply our cofactors pattern up here to this matrix of minors to get the cofactors. So the cofactors, I leave 17, 3, 40, minus 55, and minus 16. Leave all of those alone. And I change the sign of all the other 4. So this becomes a 9, 14, minus 35, and a minus 7. And that is my cofactors matrix. Then I need the transpose of this. So changing the columns into rows, I get 17, 14, minus 16, 9, 3, minus 7, minus 55, minus 35, and 40. Then the final step to give my final answer, the inverse of A is equal to 1 divided by the determinant, minus 25, times the matrix of the transpose of cofactors, 17, 14, minus 16, 9, 3, minus 7, minus 55, minus 35, and 40. And unlike the example, this is not a very easy thing to put into the matrix, so I'm just going to leave it in front like that and finish there. This is the inverse of the matrix A. If this is a simple number, like maybe a half, or 2, or 1, or minus 1, or something like that, then I would do the multiplication. Next example. A and B are non-singular matrices. I need that in here just to be clear that they do have inverses, so that we can talk about their inverses. If they were singular, then we wouldn't be able to talk about their inverses because they wouldn't exist. Prove that A times B, the inverse of that, is equal to the inverse of B times the inverse of A. And remember, the order is important here. So inverse of B times the inverse of A is different to the inverse of A times the inverse of B. So part of what we're proving is that the order AB changes to BA when you open out this inverse bracket. In order to do this, I'm not going to use an example matrix and show that it's true. I need to prove it's true. So I'm going to be using matrix algebra. So let's start by applying AB to a matrix, let's call it M. So if I apply the matrix transformation AB to M, I can have brackets here like this, but those brackets don't really do much, because in matrix multiplication it has to be this first and then this. So I'm applying matrix B and then applying matrix A. And let's say that equals N. Now if I want to invert this matrix multiplication, I can apply the inverse of A on the left. So the inverse of A must be on the left. And then here it becomes IBM, and here it stays on the left of the n. And then of course I times B, this just becomes B. Then I can do the same thing with the inverse B on the left, the inverse B on the left of the inverse of A here. That becomes IM, which of course just equals M, like so. Now if we really wanted to make it super clear, I could say let AB equal some particular thing like G. Apply that to M, and then the inverse of G applies there. And it just makes it that little bit clearer that it doesn't matter that there's two matrices here and two here. If I say let AB equal G and go through the process, the usual process, we get the inverse of G here. So the inverse of this in brackets is equal to this here. And if you wanted to put brackets there, you could. Therefore, the inverse of this is equal to this. And there are two easy ways to remember this. The first is that it is pretty much the same as the result we had with the transpose in a previous video. The only difference between these is that this obviously cannot be applied to singular matrices because singular matrices don't have inverses, whereas this can be applied to singular matrices. But the comparison there makes it easy to remember these two. The other way to remember it is by thinking what this is. We're applying potentially a transformation here, and let's make it a little bit silly. Let's call this putting on your socks, and then here putting on your shoes. When you come to undo that, which is what the inverse transformation is trying to do, you have to take off your shoes first before you can take off your socks. So there's a little slightly silly way of remembering this. Okay, our final example. The matrix A equals this, and the matrix B is such that the inverse of A times B is this. Show that the inverse of A is equal to A. Okay, an important point here in this example is that if you can do this without actually finding the inverse of A, then that's probably a good way to do it. Because finding the actual inverse of A is a long process, as we've seen in this video. What I can do here, instead of actually finding this and going, oh hey, it's the same as this, is to use matrix algebra. If this is true, and I multiply on the right of these, then on the left-hand side of the equation, that becomes I. And on the right-hand side of the equation, A times A, or A squared. So this statement is equivalent to this statement, which means if I multiply A by itself and I get the identity matrix, then this must be true. And that's going to be much quicker than finding the inverse of A through that long process that we had. So all I'm going to do here is multiply A by itself, and hopefully we get the identity matrix. If you are going to use this method in an exam, this part here is very important to include. This is your justification to the examiner as to why multiplying A by itself, giving you the identity matrix, is proving what they want you to show. Don't skip that section with the algebra there. So if we do this, first row, first column, we get 4, 0, minus 3. 4 minus 3 is a 1. That's a good start. Minus 6 plus 3 plus 3 is indeed 0. And 6, 0, minus 6. Yeah, it's looking good. 0, 0, 0. 0, 1, 0. 0, 0, 0. Final row, first column, we get minus 2, 0, plus 2. 3, minus 1, minus 2. And minus 3 plus 4 gives me a 1. So yes, this is true, which means this is true, which means this must be true. So without going through the long inverse matrix process, we have done part A. Similarly for part B, finding the inverse of B, we can do this without inverting anything by considering some matrix algebra with the result that we had on the previous example. We know that the inverse of AB is equal to the inverse of B times the inverse of A. And if we multiply A on the right of both of these sides, we get the inverse of A times A, which is equal to I, so that becomes the inverse of B. And that's useful because we already have this matrix from the question and this matrix from the question. So to find the inverse of the matrix B, we just need to do a matrix multiplication. So we've got on the left 8, minus 17, 9, minus 5, 10, minus 6, minus 3, 5, minus 4. And on the right, matrix A, and I cleared that matrix algebra to make room for this, but again, in an exam, you would need that matrix algebra to show why this is going to give you the inverse of B. Okay, this is going to take some time. First row, first column. Minus 16, 0, plus 9. We have minus 7. 24, minus 17, minus 9. It's minus 2. Minus 24, 0, 18. It's minus 6. Second row, first column, 10, 0, minus 6 is 4. Minus 15 plus 10 plus 6 is 1. 15, 0, minus 12. 15 minus 12, 3. Third row, first column, 6, 0, minus 4. 6 minus 4, 2. Minus 9 plus 5 plus 4 is a 0. And the last one, 9, 0, and minus 8. 9 minus 8 is 1. So here is the answer for the matrix inverse B. Final note is that some scientific calculators, along with a vector mode, have a matrix mode. And in matrix mode, you can actually get the inverse of a 3 by 3 matrix directly off of your calculator. If you know how to do this, and you're confident on how to do this, it can be a quick and easy way of checking a very long process in your exam. As usual, you can't just do that in the exam because you need to show your process, but in terms of checking your answer, and being confident that it's right. If you've got a calculator that will do this, it's worth learning how to do it. And you can practice all of this with questions from exercise 6C. And maybe I'll see you in the next video.